this video I'm going to go over how to solve numerical ordinary differential equations using the Runge Kutta order 4 method. So this method is a bit more accurate than the forward and backward Euler method, which is explained in previous videos. And this is for the same value of h, so the step size, which is usually 0.1. So this method is more time consuming, as you can see by all the equations required in the method. So it's more accurate but more time consuming. So we're going to proceed with an example using all these k values for the next step. So you have dy over dx equals minus y plus x plus 1. You might have noticed this is the same differential equation we used to solve using the forward and backward Euler methods, just so you can compare the results and see the difference. So we have the initial values y0 equals 1. So we know that y0 is 1 and x0 is 0. So it says determine y 0.1. So we're only going to do this iteration once, just because the step size is 0.1 and it's quite exhaustive doing all this, so we'll just do one example. So we're going to calculate all the k's. So this is how to calculate all the k's. So yeah, we would need to find the values to put into the function to find k1, and then this is how you would find the values to put into the function which makes k2, and so on and so on. So if we start with k1, so k1 equals the function of the initial x and the initial y. We have the function here as well. So by putting the initial y and x in, we have minus 1 plus 0 plus 1, which gives us 0. So k1 is 0. If we do the same for k2, so you might have seen from here that k1 is needed in k2. So you need this to work out this, to work out this, to work out this. So to work out k2, the formula is the initial x plus h over 2, which is the step size. Then we also have the initial y plus h multiplied by k1 divided by the step size. Divided by 2. So when we calculate that, the initial x is 0 plus 0.1, because our step size is 0.1. 0.1 over 2 is 0.05. And then we calculate the y. So this is 1. 1 plus h is 0.1 multiplied by k1. k1 is 0 divided by 2. That gives us 1. So when we input x and y into our function, we have minus 1 plus 0.05 plus 1. So that gives k2 a value of 0.05. Now we do the same for k3. To calculate that, we needed the initial x plus step size over 2. Then we have y plus h multiplied by k2 all divided by 2. When we calculate that, the initial x is 0, step size is 0.1, so 0.1 divided by 2 is 0.05. And then for the y, so y0 is 1 plus h, which is 0.1 multiplied by k2. k2 is 0.05, all divided by 2, which gives us 1.0025. Then when we input x and y into the equation, we have minus 1.0025 plus 1 0.05, we have 0.05 here, plus 1, which gives us 0.0475 for K3. For K4, we have the function, and you calculate this side using the initial x plus h, and then use the initial y plus h multiplied by K3. So the initial x is 0, and then the step size is 0.1. And then for y 0 is 1, plus h multiplied by K3. K3 was 0.0475. That gives us y of 1.00475. So when we input that into our function, we have minus 1.00475 plus 0.1 plus 1. That gives us 0.09525. So now that we've worked out all of our values of k, we can plug them all into this equation to work out y1, or in this case y, when x is 0.1. So we have y is 0.1 equals the initial y, which was 1, plus 1 over 6 multiplied by h, which is the step size, and that's all times by k1, plus 2 multiplied by k2, sorry. So 2 times 0.05 plus 2 multiplied by K3, and then plus K4, which is 0.09525. If we put that all in the calculator, we have 1 plus 1 over 6 multiplied by 0.1, and that's all times by 2 times 0.05 plus 2 times to 0.0475 plus 0.09525. That gives us a value of 1.0048375. So y at 0.1 is 1.0048375, and x at 0.1 is 0.1. And that's it. That's how you use the Runge Kutta method.